Okay, so our next presenter is Mudit Agarwal, two-photon calcium imaging study of spatial variation in responses to cross-orientation stimuli in macaque primary visual cortex. Thank you.
Hello everyone, my name is Mudit, and today we'll be taking a deep dive into the monkey's visual system. We'll be covering cross-orientation interactions in macaque. Now, the problem of cross-orientation interactions has been something for the past 50 or so years. We had Morone in 1982, Bonds in 1989, and Heger in 1992. The basic idea is that a neuron has a preferred orientation. What this means is in the visual cortex, a neuron likes perhaps this edge, this direction, and then another neuron might like an edge in a different direction, which is like this. So what visual scientists saw was that since the neuron likes this, and the neuron that likes this does not like the orthogonal direction, we essentially see is that if we combine it, we should theoretically have a linear match. So in other words, a response to a horizontal edge and a vertical edge, as you can see in the plaid image right there, that should have the same as a sign. However, from 1992 with the cat, that was not the case. And this is coined cross-orientation suppression. So the question now lies is, for this study, does cross-orientation suppression depend on cortical depth in the primate V1? To do this, we followed a calcium imaging study. Basically what calcium imaging is that when you have a neuron, which essentially has a calcium influx when it's excited, a calcium imaging study takes this and really sees where each neuron is excited and then records that. So what we did was we took the macaque and we placed a window, as you can see right here, and we essentially took a laser and we imaged from 141 UM down to 580 UM. This was done by a plane-wise method, which is around 28 imaging planes. And so with that, per plane, we're able to see something like this, and each of these ROIs, which are neurons, we're able to come up with 4,785 neurons through the entire depth. And then we're also able to come up with around 171 neurons per frame of view. This was all done on one macaque, and the reason we did this as opposed to other methods, calcium as opposed to like electrode methods, is that electrode methods are relatively good for the deeper depths, which is over here, but the two-photon method of calcium is much more efficient for the shallower depths, because when the monkey breathes or so, the tissue actually moves up and down, and electrodes aren't so good at these earlier depths. Additionally, we're able to see a bunch of neurons like this, rather than having to like poke each neuron to get a response. So going back to the orientation, each neuron has a preferred orientation, and this image over here shows that. So this over here shows the preferred orientation for all the neurons in the mass that we looked at. And we see this through a tuning curve, which is represented over here. Now, this black thing over here is the response to the sine curve that we saw on slide number 2, and this blue one over here shows the response to the plaid curve, which is also on slide number 2. So basically what we see here is the neuron over here really likes the direction 0 to 90. This is the highest fluorescent response, and 180 to 270, which is the second highest. So it really likes some things in the direction there. And then with the plaid, which is just the orthogonal, we have now 4 versions of that. And that sort of leads to our predicted, which we essentially took the sine and we moved it 90 degrees, added it onto itself, and we have this predicted method. So with that, we had 2 metrics based on this entire picture. One metric measured the overall light difference in like how high one was over the other, so that was metric P, and we had the other metric, which is metric C, and metric C was just a classic Pearson correlation, which is the shape. So when we look at this one over here and we compare plaid and predicted, right now we see that the plaid has a higher response than the predicted. This signifies facilitation overall, which is a p-value greater than 1. And then for the shape, it would just be the Pearson correlation. So that would be how that's computed. We took these 2 things and we computed it versus depth. So we had the p metric versus depth, and we had the c metric versus depth. And so what we see here is a strong negative correlation when we take p versus cortical depth. And so what this means is, at shallower depths, we see something called facilitation, which means that the, like over here, as we can remember from the formula, the plaid is greater than predicted. And as we go deeper, then we have suppression, which means that the predicted is greater than the planned. And similarly, as we go for metric C, this is a strong upward trend with R value greater than 0.8. And so that means as we go deeper into the macaque, the shape becomes more like the prediction, and so we see a roughly similar shape from the prediction and the plaid's response. So with these strong metrics, and as you can see here with a R value of negative 0.71 and R value of 0.80, our question now is this like because of something? What's really causing these sort of discrepancies? And so, as we know, there are many things that co-vary as we go deeper with the depth. For example, SNR, ROI, size, OSI, spatial frequency, baseline, half width, all of these things are possible like covariances. So what we did was something called a within sites analysis. We started by plotting the prophesized covariance with depth. And then we went from a site-to-site basis, which is the original FOV. We looked at it for every single FOV, plotted its significance against the metric, and we looked at it for both the metrics. So let's take baseline, for example, in this. So as we go deeper with calcium imaging, what we need to do is we need to increase the overall amount of power that the laser has. This is because as we go deeper, there's more tissue, and so we need to really see like more things. So with that in mind, what we did here was, you can see over here, it's an upwards trend because the overall baseline is increasing. And so when we looked at it from a perspective with the within sites analysis, what we see in metric P is that there's not much correlation. However, in metric C, there's a little bit over here. This being negative and this being positive, and as you can recall from the previous slide, metric C being positive, proves that if this wasn't actually a control and we're not looking at this, our trend would actually be stronger than what it's actually showing. And that's basically the same narrative that happened with each of these ROI size, SNR, OSI, SF, baseline. And the images, of course, can be shown there on extra slides towards the end. So overall, what we see here is essentially we have a gain, which is metric P. And as we go deeper, we shift from facilitation to suppression. And as we go from deeper, as we go from shallow to deeper for metric C, we see a much more linearly predictable shape in the sense that metric C is increasing as well. Overall, these two things are negatively correlated, and therefore with a R value of 0.56, we think that these are linked. That means that, in other words, based on this data, we think that facilitation is essentially the reason why metric C is actually lower, and then as we go deeper and the facilitation drops and becomes suppression, metric C will be higher. This is sort of a hypothesis that we have for the mechanism for one animal, but the depth grading itself, as you can see in this image, is the true finding that we're getting from this. Overall, there are limitations to this, of course. This is all done on one macaque in layer 2-3 only, because this is a calcium photon imaging experiment, so we can't really speak about the layers 4 and the further layers, which are much more better accustomed with a electrode. And furthermore, this is a calcium imaging study, so this does have a slower and indirect signal, not a simple spike as we would see with an electrode study. But the take-home message still remains real. This is depth dependent within the L2-3 layers. We see a really strong trend. We also see that there is a relatively negative relationship between P and C. P falls, C rises, and they're linked. And furthermore, this is a robust analysis that we see with our confounds, and it still survives those. Overall, our next sort of vision with this in mind is that we're trying to relate the gradient to the orientation map structure, which means that we're trying to look for patterns in the cube, and we're trying to see exactly where pinwheels can form, and more analysis with local homogeneity index. Furthermore, that this is also just a preliminary part of a much larger study. We were working with the Allen for getting a serial EM reconstruction and connectivity. So what we see here is a really strong depth gradient with P, and we see it how it's able to survive every single measured confound. However, with the serial EM construction and connectivity, we're able to get a synaptic wiring and as well as see how each neuron is connected. What this allows us to do is now connect physiology to anatomy, and what that allows us to do is gain a much more better picture of what this P metric is in a wider lens. That leads us to our final question, which we plan to answer soon. That does depth gradient in P that survives every single confound reflect changes in inhibitory wiring across layers 2 and 3? Thank you.
We have a couple minutes for questions.
Yes.
Really nice talk. What was the rationale for, you said you had about 176 neurons in each of the 28 lanes.
It was about an average.
What's the rationale for averaging all the neurons together? And do you have neurons in each plane to kind of buck the trend of depth? Like, or is it pretty homogeneous across the same plane?
So the entire analysis was based on a depth correlation, right? So essentially each of these frames of views are at a specific depth. So in essence, it wouldn't make sense to average them. But we also computed like a within frame analysis, as you can see over here. This is within each frame, so there's no like exact depth. And so we looked at the correlations with each neuron by point there. So it's like we looked at both. So technically we have the average and we have the non-average. Yes.
Do you have a proposed circuit mechanism for what's mediating this? Or it survives all the confounds, so it's not related to any of the stuff that you looked at, but it must be related to something.
Correct. So we don't have the exact thing by the Allen yet. This is eventually going to be done. So until we get that, it's too early to say anything. Currently what we're trying to do is we're trying to look at the possible pinwheels from this graph and multiple other graphs that look similar and trying to see if there's a trend there. Right now we don't have a actual like defined mechanism for why this is occurring. We know it's occurring, we know that it's relatively big with the strong R values, but we're trying to figure out why, and that's our next step.
And how far do you think it would go? You measured through layer 2, 3. Do you think the trend would continue if you could measure deeper?
We would need an electrode study to do that because one of the biggest problems with calcium imaging is that it only works on like the shallower depths, so it only works on layer 2, 3. So there is a chance it could, and there's a chance it could, and we would need more data for that.
So a lot of the input to 2 and 3 and B1 is from layer 4, right? And so there could be differential, as you're getting more superficial, differential innervation as you go further and further superficial.
Correct.
It could be very nice in that way.
Yes. Yes, there would be a need for electrophysical.
Absolutely, yeah. Very good, very impressive. Any further questions? All right, okay, so thank you very much.